So we've made it to section 2.2. First section of chapter 2, we talked about quadratic functions. In this section, we're going to talk about polynomials. So here's a little bit of reading in the way of polynomials. And our first definition is referring specifically to a certain type of polynomial, a mononomial. Notice the prefix mono, and that simply refers to the fact that this particular type of polynomial has one term. But in order for it to be a polynomial, there are other conditions. N, the exponent of the variable, must be a non-negative integer. And we simply only have one variable, x. A, as mentioned in the previous chapter, is a coefficient. So with example 1, we're simply going to run through this list of expressions. Here is the first one, here is the second one, and we're going to decide whether that particular expression is a mononomial. The first one, and I'll circle them, circle monomials, I didn't even spell that right, nomials, polynomial with one term. 3x squared is a mononomial. We have one variable, it has an exponent that is positive, and it's an integer. 3 is the coefficient. This one is not. 4x to the negative 3, because the exponent's negative. We only want non-negative integer exponents. I will circle the next one. 5.8x to the fourth is a mononomial. 7x to the 3/4 is not. 3/4 is 0.75. It's not an integer exponent. The next one, we have a negative coefficient, but that's okay. We have our variable x, and it's raised to 4, a power of 4, and 4 is a non-negative integer, so this is a mononomial. The next one is a mononomial. We could calculate 6 to the 5th power, and whatever that number is would simply be our coefficient. I will calculate that real quick. 6 to the 5th power, there, 7,776. And then we just simply check our exponent, 3. It's positive, and it's an integer. And here we have the square root. And another way to write this expression would be 4. And here we have x squared, which is okay, but then we have an exponent of 1/2, and 1/2 is 0.5. It's not an integer. So if you see radicals, more than likely it is not a mononomial, or a polynomial for that matter. So remark 1, it can be shown that if x equals 0, then we have x, or x does not equal 0, then x to the 0 equals 1. We simply run into that situation of something divided by itself. So for instance, over to the side, if I took an x squared and I divided it by itself, x squared, then the quotient rule of exponents simply states that I can, since the variables are the same, we have the same base, then I can combine the exponents through subtraction, and that gives me an x to the 0. Well, something divided by itself is 1, and therefore x to the 0 should be 1 also. Okay. Definition 2, we can create a polynomial, which means that it's has multiple. The prefix poly just means that we have multiple mononomials or single term polynomials through addition and subtraction. The term with the largest exponent is our leading term, and then the exponent of that particular term is what we call the degree of the entire polynomial, and then its coefficient is the leading coefficient. So example 2, we are going to pick out these different properties of the polynomial. So what is the degree of p? Well, we scan through our terms. All of them have positive integer exponents. This can be written as x to the 0, and above that simply explained that this is considered to be a polynomial as well, or a mononomial. So we have a mononomial, subtract a mononomial, subtract another one, so there's 4 mononomials to create this one polynomial. One way you could look at it. And all the exponents are positive and integers. So what is the highest exponent? That's our degree. Highest exponent, well, that would be the 7. So the degree of p of x, just to say the same thing another way, is 7. What is the leading term? Well, the term that had the exponent of 7 was 13. So the leading term is 13x to the 7th. What is the leading coefficient? Well, that would just simply be the 13 itself. So the coefficient refers to the number, the factor of the mononomial, the number factor. And so we have several coefficients in this polynomial. 3, -5, 13, and 5 are all coefficients. But we go with the 13, not because the 13 is the biggest coefficient, but because the 13 is the coefficient of the term with the highest exponent. So leading term is 13x to the 7th. Leading coefficient is the coefficient of that term, 13. Now it says we want to write polynomials in descending order, meaning that we start with the highest exponent and work our way backwards, listing all of the other terms. So the first one, the highest exponent term, 13x to the 7th. Then, so I'll strike these out as we write them down. And now to the right, I want to write -x to the 4. We didn't have a 6 or a 5, and so we make our way down to 4, and then 3. There is no exponent 3, but we do have a term that has an exponent of 2. So the next term we write down is 3x squared, and then finally our constant term always comes last, plus 5. So this is p of x in descending order. This q is not a polynomial. Radical typically not a polynomial. I say that because we could have a polynomial, and I'm making this one up, let's call it r of x, and r of x could equal the third root of x to the third. And if we simplified this radical expression, then we would simply get x. And so this would be a polynomial. However, if I write a separate polynomial, n, just to call it a name, and I wrote the square root of x squared, then I'd have the absolute value of x, and that is not a polynomial. This, and we'll say more about this later, but the absolute value of x has a sharp point at the origin, so not a polynomial. What about this r, which is a different r than the one that I listed over here? We check the exponents. 4, 5, 3. Exponent of 5x is 1. Here we have a fraction, but that's simply the coefficient of this term. The exponent is 2. It's a positive number. 2 is a whole number, or you could say it's an integer. And then 12, which is just the constant term, and we do consider 12 to be a monomial. So r is a polynomial. R is a polynomial. What is the degree? Degree of r is, we simply seek out the highest exponent, and that is 5. Polynomial of degree 5, the leading term is the term that had the exponent of 5, so that would be minus 2x to the 5th. And then what is the leading coefficient? Well, it's a negative 2. It's simply the number factor of the term, negative 2, or basically the number that sits in front of the variable. And our last one, t of x. T is a polynomial. Well, it only has one term, so we would say the degree is 0, or degree equals 0. The leading term, well, it only has one term, 37, and the leading coefficient is 37. Picking it back up with the next page, we have little f of x, and it is a polynomial because we have the exponents 2, 1, and this constant term could be written as 1 times x to the 0. So all positive integer exponents. What is the leading term? That is 3x squared. It's the term with the highest exponent. Well, what's the degree? The degree of f of x is 2. It's the exponent of the term that has the highest exponent. What is the leading coefficient? That would be 3. And this polynomial is already in descending order. If we count backwards from the highest exponent, 2, 1, 0, they're listed from the left to the right. What about u of x? Well, this is not a polynomial. It is because of this exponent -2. We only want non-negative exponents of our variables. U is not a polynomial. And neither is little r, because we have these variable terms in the denominator. What about little p of x? Well, we have here a polynomial times another polynomial, which happens to be itself a polynomial. So the product of two polynomials equals another polynomial. It's sort of like saying same property with real numbers. If we take a real number, say 5, and multiply it by another real number, it could be any real number, but I'll pick 4. Well, 5 times 4 is 20, and 20 itself is also a real number. However, with this being written as the product of two polynomials, we cannot just simply pick out the highest exponent with it written this way. We actually need to apply the distributive property. So I will take the 3x squared, the first term of the first set of parentheses, and multiply it by the x in the second set of parentheses, and then 3x squared times 3. And now we're done with that first term. And then I'll take the second term, which is a -2x, multiply it by the x, and also by the 3. And unfortunately I've ran out of room, so I'll just write this out again on the bottom, and I'll go through and I'll multiply these together, because 3x squared times the x I could rewrite as 3x to the third. This next term can be written as a plus 9x squared. This one, that term, can be written as a minus 2x squared. And then we have a minus 2x times 3, which is a -6x. And so now I've finished with the minus 2x, and now I distribute the -1, which gives me a -1 times x minus x, a -1 times a positive 3, minus 3, some of these terms can be combined, such as these two, and then these two are like terms. So in the end, I would write p of x as 3x squared plus 7x, oh, that's supposed to be x to the third, and then I have 9 minus 2, 7, and x squared, the common variable part. For the next two, I have a -6 and a -1, so this would be a minus 7x. These two 7's don't cancel out though, because this is an x squared term and that is an x term. They're not like terms, so we can't combine the 7's. And then we have a minus 3 as our constant term. And we already have the polynomial written in descending order, 3, 2, 1, 0, according to the exponents. We can now pick out the degree. The degree is the highest exponent of the variable 3. The lead term is the entire term that involved that exponent, 3x to the third. The leading coefficient is the coefficient of the leading term, 3. And so that completes all the information that we were asked for P. So remark 2, sum, difference, or product of two or more polynomials are also polynomials. We saw an example of the product there with little p of x. Evaluating a polynomial, if f of x is given, then f of c is obtained by substitution. So we've seen this several times throughout the workbook already. We want to evaluate f at a particular point x equals -1. So we simply walk through the polynomial replacing x with -1. I always like to put parentheses around the -1 that I have to insert inside of a function. So we have 2 times x to the 4th, so I write -1 to the 4th. Then there's an x to the 3rd, so -1 to the 3rd. And then the third term is -3 x squared, so -1 squared, and only the -1 is squared. So with f of -1 written out, I will go through and apply the exponents. -1 raised to an even power is simply a +1. This next term has an odd exponent, so that would stay -1. Now this -1 is squared, which is even, and so this piece, -1 squared, would be +1. But I multiply that by the -3 in front, and so it simply stays negative. Negative times the positive equals -3. Here I have a -7 times a -1 plus 7. And then I just simply write out the plus 12 to the side. I have 2 times 1, passing back through the expression. 2 times 1 is 2, plus a -1 is subtract 1, then I subtract 3, add 7, add 12. So 2 minus 1 is 1. Take away 3 more, I get -2. 7 minus that 2 is 5. 5 plus the 12 results in a 17. So f of -1 equals 17. We have seen that many times before. We simply replace the variable with the number that we're given inside the function notation. G is a different polynomial. G is 3x to the 3rd. Replace the x with 2. Raise the 2 to the 3rd power. Then the second term is 2x squared. So I write 2 times 2 squared. Minus 5 times 2 plus 1. 2 to the 3rd is 8. 8 times 3 is 24. 2 squared is 4, times 4 is 8. 5 times 2 is 10. Subtract 10, and then add 1. 24 plus 8 is 32. Take away 10 from 32, I'm back to 22. And then if I add 1 to 22, I get 23. G of 2 equals 23. Bottom of the page, we have remark number 3, And what does it say? Polynomial of degree n. In general, it can be written this way. An is the coefficient of the highest or the leading term, the term with the highest exponent. An minus 1, this represents a single number. This is a coefficient, as a to the n, or a sub n, was a coefficient. And then a sub 1. So these are coefficients, and then according to the degree, we could have, with a polynomial of degree n, we want all the other exponents to be less than that, so we could have a polynomial with the exponent of n minus 1, n minus 2, n minus 3, depending on how big of a number n actually was. And then eventually we're going to run into the linear term where the exponent is 1, and then in the end a sub 0, which indicates our constant, and a sub 0 is simply just a number. Then as long as we require a polynomial of degree n, we simply say that we don't want the coefficient of that term, the term with the exponent of n. This gives our degree. So if this is the term with our degree, then we don't want a to be 0 because it would cancel that term out, and so our polynomial would actually have a different degree other than the one that we wanted, which is n. Alright, we have already seen degree, leading coefficient, leading term. Example 4 simply wants us to write out this capital P polynomial in descending order and identify all the coefficients, etc., etc. So P of x in descending order would be written with this term first, 5x to the 6. The 6th power is the highest exponent among all the exponents. Do we have a 5th degree term, or a term with the exponent of 5? That one comes next. So we're simply counting backwards from 6. 6, 5, 4. Here is our term with a power of 4, minus 2x to the 4th. So I scratch that one out. 4, 3, 2, 1. So x to the 3rd comes next. Then we have plus 3x squared. 3, 2, 1. And this is our term with the power of 1 for the variable, plus x. And then we write plus 12 on the end. So pretty long polynomial. What is the degree? Degree of P of x is 6, and I simply picked up this 6 here. It's the highest exponent of all the variables. What are the coefficients? A, n. In other words, n is always considered our degree. And so with the degree of 6 for polynomial p, we can, instead of writing an, we can write a 6. Well, a with a subscript 6 simply represents the coefficient of that particular term. So we find our term with the power of 6, and we take the coefficient, which is 5. And we had a term for every exponent counting backwards from 6. 5, 4, 3, 2, 1, 0. So we will have an A5, and it is negative 7. Exponent 5, what's the coefficient? Negative 7. We have an A4, it's negative 2. We have an A3, that would be 1. Here is the A3 term, or the term with the exponent of 3, and there's just a 1 there. A2 would be 3, A1 would be 1. So the subscript tells us the exponent of the variable. Here is the variable with an exponent of 1. We look in front, pick up the coefficient, and that was 1. And so in the end, we have A0 equals 12. A0 is our constant of our polynomial. And so you're not always guaranteed to have one of each. Some of these, in some cases, can be 0. So if we were missing a term, then that particular coefficient would be set equal to 0. So just to give you an example, let me write a different polynomial. Let me say m of x. And let's say that we had this polynomial was 3x to the third minus x plus 2. Well, we'd have an A3. It would be 3. But then A2, there is no variable with a power of 2, so we'd say A2 is 0. And then all the other ones, counting backwards from 3, we have, other than the 2. A1 is a negative 1, and then A0 is a positive 2. Remark 4, polynomial of degree 0 is a constant. It's just a number, so we could write some examples of that. P of x equals 3. Or P of x equals negative 5. We simply just write a number as a polynomial. We don't include any variables. Polynomial of degree 1 is a linear function. We have an x to the first power, and that x has the highest power variable in the polynomial. So it is of the form ax plus b, and if we graphed it, it would be a straight line. So some examples of that would be p x equals 2x minus 1, a slope of 2, a y-intercept of negative 1. We can write p of x equals negative 3x plus 2. So a slope of negative 3 and a y-intercept of 2. So those are linear functions. Then we have the quadratic ones, which we talked a lot about in section 1 of chapter 2. And we saw that we had a, b, and c. A is the coefficient of the squared term, b is the coefficient of the linear, and c is just the constant of the polynomial. Definition 3, a root of a polynomial. So if we plug in the root of a polynomial, for instance, here we're saying c is a root. If c is a root, then p of c will simply zero out our polynomial. We put c in the place of x and we do the calculation, we get 0. So example 5, we have x equal 2. We want to show that it's a 0 of this polynomial p. So we calculate p of 2. Replace the x with 2. 3 times 2 is 6, minus 6 gives us 0. So 2 is a root of p of x. What about 5? Well, if we calculate p of 5, we have 3 times 5 minus 6, 15 minus 6, and we calculate 9, which does not equal 0. So x equal 5 is not a root of p of x. B says show that values x equal 1 plus 2i is a 0 of p of x. So here for our root we have a complex number. It's complex because we see the I component. So 1 is the real part, and then 2i is the imaginary part. I'll just simply write imaginary here. Sort of abbreviated that. Imaginary. So to do this properly, you have to remember that I squared equals a negative 1. And we're going to have to square this x. P of x has an x squared component in it. So you definitely need to know that I squared is negative 1. We calculate P of 1 plus 2i. That equals 1 plus 2i squared minus 2 times 1 plus 2i plus 5. So if 1 plus 2i is a root of this polynomial, you'll probably be surprised that all of these i's will end up canceling out. If we square 1 plus 2i, we get 1 plus 4i. We simply multiply the two terms and double it since we're squaring a binomial. Otherwise you could expand this and fold it. And then we square 2i, giving us 4i squared. We distribute the 2 here and we get minus 2 minus 4i, and then we have a plus 5. Already we see that the 4 i's will cancel. Here's a plus, there's a negative. If we rewrite this, we have 1. I squared is replaced with a negative 1. Then we have minus 2 plus 5. This is a minus 4. So now we have 1 minus 4 minus 2 plus 5. Well, 1 and 5 are 6, and then negative 4 and negative 2 are negative 6. So this does turn out to be 0. So P of x has a complex root. If you were to graph this, you would see that there's a dip in P of x, but it doesn't drop below or above the x-axis. It doesn't cross the x-axis. So what are some properties of zeros of a polynomial? Polynomial of degree n has at most n zeros. So for instance, if I wrote f of x equal x to the third minus 2x plus 4, the most zeros that I could have for little f would be 3. Some zeros may be real, some complex. Complex zeros come in pairs. So in other words, little f could have 3 real zeros, or it could have 2 complex zeros and 1 real zero. The factor theorem says that a number c is a zero of a polynomial if and only if x minus c is a factor of the polynomial. So in other words, if we have the zeros are x equal 2, x equal negative 3, then we can actually recreate the polynomial. We could say p of x equals x minus 2 times x plus 3. And actually there could be many types of polynomials where these are the zeros. We could square either one of these factors. But this is just simply stating that if one of the zeros is x equals 2, then I definitely have a factor of x minus 2. It doesn't tell us how many that we have. Property 2, to find the zeros, we set the polynomial equal to 0 and solve for x. We have talked about solving linear equations that way, and in the previous section quadratic equations. And then if it's already factored for us, then yeah, that's easy too. We just take each individual factor and set it equal to 0. So for instance, let's say I had a polynomial r x equals x minus 2 times x plus 3 times x plus 1. It's already factored. If I were to multiply all this out, this would actually be an x to the third degree 3 polynomial, and we haven't really spent a lot of time solving for the zeros of those types of polynomials. 3, 4, 5, any of the higher degree polynomials, we usually just simply rely on our calculator. But in this case, we already have the factors, so if we wanted the zeros of it, then we just simply take each factor and write the equations x minus 2 equals 0 and solve that one. So x equals 2. 2 is a 0 of Rx. Then we take the others and do the same. X plus 3 equals 0, and then x plus 1 equals 0. So if it's already factored, the work's done for us, or at least most of it. 3. Real zero of a polynomial is in fact an x-intercept of the polynomial. Factorization of a polynomial is not possible or difficult to obtain easily. Real zeros can be estimated graphically. We've done this before. Complex zeros cannot be determined graphically. We have no x-intercepts to rely on. For instance, if you have a polynomial of degree 2, a quadratic function, and it does not touch the x-axis, there's nothing to see on the graph. Usually it crosses the x-axis, and we can use the calculator to calculate the zeros. Repeated zeros occur where a particular polynomial simply touches the x-axis, such as here and here. Okay, x equals 7. And then we also have another type of repeated zero. The polynomial sort of becomes flat at the x equals 4, sort of crosses through at a very flat slope, and so they tell us up above if the degree of the factor. So for instance, before I wrote a polynomial with zeros, if I said the zeros of a polynomial are x equal 2 and x equal negative 3, then I could write my polynomial as x minus 2, x plus 3. I know the factors. But then we could assign different multiplicities to each one of these factors. So I could, for instance, say x minus 2 has a multiplicity of 2, and maybe x plus 3 has a multiplicity, an odd one, of 3. And so keep in mind this p of x is just something that I made up. It's not actually this graph that we see to the right. This is sort of just a different example. This factor would have even multiplicity, meaning that it would simply touch the x-axis but not cross. And then this, and it would do that at x equal 2. At x equal -3, that factor has odd multiplicity. So it would become tangent to the x-axis and then cross. Tangent and cross. So what about this one that's graphed here? We could say that one of the factors is x plus 2. And you see here that we touch the x-axis at x equal -2. So I say the factor of the polynomial, we'll give it a name, px. Or maybe I should give it a different name other than the one that I did to the left. We'll call this Rx. So Rx touches at -2, so one of the factors is x plus 2. And so the power of this factor must be even, so I could say squared. Then we have another factor. It actually crosses at x equal +4. So if the factor that corresponded to this 0 would be x minus 4. It crosses, so it must have an odd multiplicity. I'll say 5. And then it crosses straight away. It just shoots straight through x equals 7, which would translate to x minus 7 as a factor of the polynomial r. And we see that it simply has a multiplicity of 1 if it crosses straight through the x-axis. It doesn't become tangent, it doesn't touch it, but not cross. And this is the most, at this point, that we can tell about this polynomial. Example 6, what does it want us to do? We want to find the exact values of all zeros, real and complex, determine which zeros are x-intercepts, find the multiplicities, also use graphical techniques to estimate the real zeros, compare them with their exact values. So we got quite a bit of work to do here. Let's get started. We have p of x degree of 3, and we're not used to working with these a lot, but we got lucky in that there is no constant term, and so each term here has an x variable, so we can factor this using the greatest common factor of x. In terms of the coefficients, 2, 5, and 12 do not share any common divisors, so the best I can take out is an x. Once I divide that out of each term, I'll be left with a 2x squared plus 5x minus 12. (2x squared plus 5x minus 12) will factor as a 2x times the x to get the 2x squared term. Then we have to play with the numbers, the last two, so that they multiply to give us 12, and then the cross products have to add to give us a 5x. So this is a little tricky. I will say minus 3 and a plus 4. So 2 times a plus 4 is 8 x, and then in between we have a minus 3x. If I add these two x terms together, I do get a positive 5x. So made a pretty lucky guess there. Otherwise, you'd have to do the AC method. So to set this equal to 0, now that I have it factored, I simply write each of the factors individually as their own equation. Set equal to 0. This one I actually have to do a little bit of work to get the x by itself. So here is 1 0, 3 halves. The other one is actually 0. We took this x over here that we factored out in the beginning, set it equal to 0. There was no work to do there for that one. And then we have an x plus 4 equals 0. You subtract 4 from both sides, and so x equals negative 4. Here is our final and third 0. And we only have 3 zeros because our degree of our polynomial is 3. So we can have at most 3 zeros. So let's look at the graph. 1, if we look at these zeros, we see the exponents for each factor is 1. So multiplicity for each one is 1. Multiplicity, and I'm going to run out of room, 1. Each one had a power of 1, and the exponent for these factors is written immediately outside of the parentheses. So for 2x minus 3, we have this 1. For x plus 4, we have that exponent 1. So multiplicity of 1, multiplicity of 1 for each. So in other words, it's not going to be tangent to the x-axis at those locations. It's going to pass straight through them. If I bring up my calculator, we can verify that graphically. I'll type in 2x to the third plus 5x to the third, or the second, and minus 12x. Enter. Graph. And here we see our 3 zeros. I will calculate this first one, and I'll leave the other ones up to you. Second, calculate 0. There's my cursor, and I want to go to the left of the first 0 there. It is the smallest. Then I go to the right bound, hit enter, and enter a third time, and I get 0 of x equal negative 4, which was this one that I calculated at the bottom of the page. This one crosses through the origin, so that takes care of this first one, x equals 0, and more than likely this last one on the right is our x to the 3 halves, or x equal 3 halves. What about p of x? Well, luckily we don't have to factor this. That would be a total mess. We'd have x squared times x would be 3 times x squared here would be another 2 added to our exponent, which would be 5, and then 5 plus this 2 would cause p of x to have a degree of 7. So 2, 4, 5, 6, 7, 8. Okay, let me recount that. Maybe that's 8. 2, 4, 2, 3, 4, 5, 6, 7. Yeah, 7. I don't know how I miscounted that. But p of x has a degree of 7. That would be very difficult to factor, if at all possible. But we have the factors already worked out for us. So I simply take x minus 4 and set it equal to 0. Even though it has an exponent of 2, there's no need to do it twice. X equals 4 has a multiplicity of 2. It's even. You could say even multiplicity. The next one, the factor x plus 7 equals 0. So x equals negative 7. This has multiplicity of 1. So it doesn't become tangent, or it doesn't just simply touch the x-axis. Our next factor, x squared minus 9, we would solve this by moving the 9 to the right. We would take the square root. You'd have to remember to put plus or minus in front of the square root of 9, and the square root of 9 is 3, so this would give us two zeros, a plus 3 and a negative 3. For our last factor, x squared plus 2x plus 3, we will have to use the quadratic formula. B squared is 2 squared, so 4, minus 4, a is 1, times c would be 3. So you see right there, when we can't factor it, the discriminant turns out to be negative, and the discriminant is just simply the inside of the radical. Fancy word. 2a on the bottom, so in the end we get negative 2 divided by 2, a plus or minus. This discriminant turns out to be 4 minus 12, which would be negative 8. We place that over 2. We could rewrite this as a negative 1 plus or minus. This negative inside the square root would result in an I. And then to simplify the square root of 8, we would have a 2 and then a square root of 2, and that would be divided by 2. So in other words, these 2's would cancel, and here we see we get 2 complex zeros. 2 complex zeros. They're complex because we have this plus or minus I component. So we're going to get a dip or a peak in the polynomial when we graph it, but it will not cross the x-axis. And then with a multiplicity of 2 for x equals 4, we'll simply touch it. Now whether we come from the top or the bottom, I can't be sure of that until we actually graph it.